It's my great pleasure to introduce our guest lecturer today, Dr. Broder. Dr. Broder is the Chief Medical Officer of Celera today. He has a quite distinguished career. I'm going just to highlight 2 or 3 things. He was appointed by President Reagan to be the director of the National Cancer Institute. He was one of the founding scientists of Celera Genomics. His leadership team, the map of the Human Genome that we see there, has the imprints of his leadership and scientific mind. He was also my colleague. We had a lot of wonderful discussion and collaborations, and not in a small measure, this course, Medical Bioinformatics, was inspired by my discussions with him about how mathematical and computational sciences could be involved in clinical aspects. And maybe the last things to mention, his lab used the AZT drug, which is a major drug in AIDS research and therapies. So with great pleasure, Sam is going to talk to us about the human genome and a few statistical fallacies that are typically associated.
Thank you very much, Soren. It's a wonderful pleasure to see you again, and it's a really great pleasure for me to present to the class here. And I hope that we can have a lively discussion, and I hope we can have an enjoyable hour or so. I'm going to talk about my own personal views on the human genome, and they may not coincide with what more canonical representation of that field might say. So I'm going to present the viewpoint of someone who's actually primarily a doctor, MD person, trained initially to take care of patients and in some manner means heal the sick or prevent unnecessary deaths or premature deaths. And that will be my perspective. And that may not be the perspective that others would bring to this particular topic. So the title for my talk, and I had a little bit of difficulty coming up with it, because in part it's kind of hard to condense a classroom topic into a short sentence. But at any rate, I thought I would call it the human genome. Sequencing and assembling the 3 billion letters of code was the easy part. And there hopefully is some irony in that, because at the time, largely due to Soren and his colleagues, we were able to sequence and assemble the human genome using whole genome shotgun sequencing and assembly, a feat which was thought to be, for practical purposes, technically impossible. So there is an irony in that title. But that was the easy part, is my point. So this, as Soren alluded to, this was Celera in the summer of 1998. This was the entire company, as a practical matter. There were 4 strange or not strange looking guys assembled in the shell of a building on the Rockville Pike in Rockville, Maryland, about 25 miles from the White House. And this was it. This was the official picture. And you can see Craig and you can see me in the background, hoping that no one would ask me any questions that would reveal my total ignorance of the topic. I show this slide because this was the slide taken at the White House when Bill Clinton was the president, in which we assembled in the Treaty of Utrecht or Treaty of Paris or whatever comparable concord you wish to name, in which the NIH, Human Genome Project organizers met, and we sang Kumbaya and had a wonderful time at the White House. And this was the Celera team that went into the White House at the time. I'm showing this partially because it has a nostalgic practical value. I'm also showing it because historically it is exceedingly rare to see Craig in a tie, and it's even more rare to see Ham Smith, the Nobel laureate who helped us with many of the libraries involved in the Genome Project, wear a tie. In fact, that's the only time I've seen him wear a tie in my entire recognition of him. And the guy, a strange-looking guy on the left, is here. I want to introduce, later on I'm going to talk about the concept of stage migration. And I want you to remember the guy on the left, lower left there, as you look at it, because it will illustrate a point probably more effectively than any other metaphor. So this was the Human Genome Project announcement, the Celera part of the equation. This was a wonderful lead science article, and basically it was published in February of 2001. And an entire new era was declared. The human genome, at least a reference genome, had been essentially sequenced and assembled in large degree and could become a major element for future research. It was a very important event, no doubt about it. But one of the questions that comes up is, well, you have the whole genome, how come you haven't cured cancer? Or how come, you fill in the blanks, how come you don't know how to prevent diabetes totally? And how come you haven't cured AIDS? Or whatever the topic is. And after all, you have the genome. It is, people use different ways of characterizing it. But they all have an element of this is a revolutionary paradigm-shifting event, which it is. But then there is a logical disconnect. If it is such an important event, how come we haven't cured? How come we're not here sitting talking about something that has nothing to do with human biology and human diseases? Because all answers are in. And I'm going to try to address that in part. So you can see a series of articles that were written. Some written immediately before the genome was finally assembled, but when there was a certain inevitability about the project. And in it, we made all sorts of predictions. Here's one article that I found at random where we made comments. And the question that comes for us today is how many of these predictions of what the human genome would mean have actually come true in the approximate 9 or 10 year period since that event occurred. So here's a quotation that I took from another paper. And we can judge for ourselves, or you can judge for yourselves, how prophetic these statements were. So this was a paper that Craig and I wrote. Well, let's be candid. I wrote it, and Craig made useful comments. But this could be a good thing for Craig if you disagree with the topic, which is important. So our DNA sequence and its variation provide a special record of human evolution and the migration of populations. This was written before the genome was actually completed. So we will learn how this sequence varies among populations and individuals, including the role of such variation in the pathogenesis of important illnesses and responses to pharmaceuticals. We will localize and annotate every human gene and the regulatory elements that control the timing, tissue site specificity, and the extent of gene expression. And for any given physiologic process, we will have a new paradigm for addressing its evolution, its development, its function, and its mechanism. This will revitalize medicine by identifying important new targets for prevention, diagnosis, and therapy. So, if this were a multiple choice, do they give multiple choice exams at Brown? Do they give true, false? Do they give exams? Okay. If you had an exam and you had to answer this true or false, and only true or false, what would the answer be? I would say it's more true than not, and therefore true. And if you had to rank it by percentage accomplishment, I would say a significant percentage of what this says, insofar as it says it, has in fact been accomplished in many ways. And yet, there is an enormous gap between what we need to do and what we have done yet. And that's where some of the issues come up that I hope to cover today. The reason we have a human genome is because Craig, in part, we have a human genome because of evolution, but the reason we have a human genome sequence and assembled the reference for discussion is because Craig and the visionaries he was able to recruit, of which Soren was certainly one, were able to do what I think was, from my naive way of looking at it, technically an exceptionally difficult, if not impossible, task at the time, and probably even in retrospect. Whole genome shotgun sequencing assembly was at the outer limits of technology, and yet it was done. So, I mean, enormous visionaries, and Craig Venter certainly was one of those. I want to cover one special application that is in that arena. I'm from Celera Genomics and the Celera Corporation. These are some discoveries that have been made since the genome was a sequence and assembled, and in my opinion, in consequence of its assembly. So I'm giving this as the prelude, as a foundation for where we've come and where we might be going. But for those who have heard me speak, before, and yet are brave enough to hear me repeat the exercise, you will see that I always try to set things up. This is obviously a setup in part. I'm going to talk to you about positive things, but then I'm also going to talk to you about why we haven't done more. So I'm setting up the equation here that, yes, we have done a lot. So I'm going to describe one element. And the idea is now that there is a fully sequenced human genome to deal with, one can either use whole genome association studies, of which you no doubt have had many examples in this class, or you can use a slight variation, which is the understanding functional genomics, which is essentially trying to do an exon by exon resequencing the genome and then focusing only on the coding regions and then looking to see if there are variations and associations you can find in diseases. And by both techniques, we've chosen the latter, but by both techniques, you can make discoveries. You can make important discoveries. No question. There is no question at all. Discoveries that I think would have been difficult or impossible to contemplate prior to the genome. So I'm using this as an example. So here is an example of a gene, the kinesin-like protein, the gene that encodes kinesin-like protein 6, which was not thought to be associated with heart disease. And there's a DNA polymorphism, a SNP, in this kinesin-like protein. Kinesins essentially are like robotic proteins, if you will, that walk along tracks and carry cargo around. And there is a DNA polymorphism, a single nucleotide polymorphism that is associated with heart disease, and more significantly, in my view, is associated in many ways to responses to statins, but not by necessarily the classical canonical lipid pathways that we've heard about in over so many decades. So it provides a totally new way of looking at the problem and perhaps offers new ways of understanding the pathophysiology or even the new targets for treatment. And this is a consequence of the human genome. Here's just but one example of this. So this is a study in which one examined what's called the Prove It TIMI-22 trial. This was a study in which individuals who had acute coronary syndrome, which for the purposes of our discussion here, I'm going to simplify, is basically either a heart attack or a cousin of a heart attack. I'm simplifying, but that's acute coronary syndrome. So basically, this was a famous study that randomized people to an ordinary dose of a drug called pravastatin, a kind of a statin, versus an intensive dose of another statin called atorvastatin. And what happened is that study clearly showed that intensive atorvastatin worked better than the ordinary common dose of pravastatin. That was before the genome came in. We analyzed that study using this KIF6 carrier approach, and we found that individuals who carried one allele of the variant we're discussing here, the KIF6 719RH variant, and we actually looked and we observed that all of the benefit, all the clinical benefits, were assigned to individuals who carried this variant allele. We're using clinical endpoints. That is the highest standard you can do in a clinical trial. And the clinical endpoints were a recurrent event, death, or something related to that, another heart attack or need for restenosis repair or something. And basically, with these clinical endpoints, you could see the curves pull apart. In fact, you can see that they're actually starting to pull apart at 3 months by these clinical endpoints. However, if you look at people that are non-carriers, you don't have a demonstrable difference. So what you have here is a situation where a certain genetic endowment carried the whole population. And I'm sure you're familiar with that notion that it is possible for a particular benefit all to be confined to a certain population. And then depending on the size and the effectiveness, that population essentially can carry what you think is the total effect for the total population. Okay, so that's what we think is happening here. And what we observed was that we could not ascribe the difference in benefit to a difference in the response to what everybody thought would happen, which would be a difference in the degree of lipids or the degree of C-reactive protein, which is a kind of special, effectively a marker of inflammation. So there were differences in that high-dose atorvastatin did give a more significant drop. But there were no differences between the two carrier states, if you see what I'm saying. It isn't that we're accidentally tracking some unusual response to the lipid profile. We're tracking something that is different. We think it is related to a process called vulnerable plaque. We think it's related to a tendency to predict who is going to get vulnerable plaque rupture, and the effect of pleiotropic effects of statins, which have many effects, including against inflammation and against certain processes that go on in the endothelium. And we think that's what we're tracking. We're not tracking mere cholesterol drops or improvements along that line, which is a kind of reversal of the normal canon that people taught. I'm not saying that cholesterol or lipid profiles are immaterial to this process. But in this particular experiment, we are finding that a drug, atorvastatin at high dose, 80 milligrams a day, seems to be working in acute coronary syndrome by an unanticipated mechanism. And I don't believe, and that mechanism, one assigns who's going to derive all the benefit from statins in this context, high-dose statins. It also provides a whole wealth of opportunities to discuss brand new ways of targeting these diseases. So this is just a schematic. Why should something that normally carries cargo, that's what kinesins tend to do? I would venture to say without too much fear of contradiction that virtually everyone in this room knows more about kinesins than I do. But I can certainly tell you this. Kinesins were not big on the top 10 list of causes or related molecular mechanisms of heart disease before these discoveries. And now we have a whole new method of dealing with it. They carry cargo. They're actually neat to watch a picture of it because they actually look like a science fiction robot with little feet. I'm not making this up, that walk along tracks that seem to have headless dimensions, but like arms that will pick up something and walk on the track. It's really eerie to think that that's going inside our bodies, even now as I speak and as you're listening. Very, very, very eerie. But nevertheless, some DNA polymorphism in this probably cargo-carrying region of this protein seems to be related to heart disease and seems to be related to the mechanisms of how statins work in certain situations. Now, please, I'm not saying that high-dose atorvastatin doesn't do something through lipid profiles, but what I am saying is it's doing something beyond mere canonical lipid biology. And that would have been very difficult or impossible. So I'm going to switch gears now. So I gave you my bona fides. Yes, the human genome has yielded a number of things. I'm giving you a concrete example of the kinds of things, and there's lots of other things you can talk about, the kinds of things that it made possible. But I'm now going to move into another area, which is now the really dominant theme that I want to cover. And hopefully some of you in this room are going to solve some of the problems that I'm going to identify. And the problems are, it can be reduced to the notion of, well, why does it take so long to do anything? How many of you are in a pre-med course or may intend possibly to become a physician someday? One. I'll bet more of you will do it, but at least one. I guarantee you're going to hear the following from relatives and friends as you go to medical school or in your early training. Why can't we do more about this disease? Or how come we're not doing that? What's the problem? And they'll hold you personally accountable, by the way, just in case I'm just preparing you. No matter what, your friends and relatives are going to come to you at a party and they'll hold you personally responsible for the lack of progress. Okay, so I have two observations from a doctor's perspective, that being me. Statistics as a discipline is not intuitive, and it is hard. Actually, this is going to be three observations, but I'm going to call this. And then conditional probability is even harder. It is really hard. It may seem easy because no doubt many of you are facile and you can handle the issues. But conditional probability, under the right circumstances and the right presentation and in the right milieu, can stump full professors of mathematics, as Soren no doubt has shown you, or will show you. And then there's this quotation. It's obligatory to have some quotation from Henry V or from Hamlet or something, or some Greek thing, and I'm choosing to do this in these talks. So basically, there's a lot more in medicine and statistics and biology than you might think. And in particular, many assumptions that take the view of being almost axiomatic, not worthy of further discussion, so fundamental that they can't be analyzed may be incorrect. So that leads to some issues. So statistics. I show this slide because none of you in this room is old enough to have actually seen or even heard of this kind of advertising. I, however, do not fall into that category. So I can remember that within my lifetime, that basically cigarettes were advertised not only in the kind of way that we give you a warning, smoke at your own, the way they do now, the pro forma, smoke cigarettes and you will die, so that's it, now please buy our brand. Okay, that didn't used to exist. In fact, the opposite was true. The opposite was true. There was a time when cigarettes were promoted as a health benefit, or if not a health benefit, one step below a health benefit. I'm making none of this up. Okay, so what were the tools that were used? This is really cool. First they used a symbol. There was an era where, believe it or not, people respected authority. And there were certain figures, governmental figures in particular, that people believed in. There were people that worshiped Franklin Roosevelt. If you said a bad word about him, you were going to get beaten up. And people felt that way about many government officials or other officials at high rank. And there was a belief in authority figures, which was capitalized by the cigarette companies at the time. And at the time, the highest authority figures that people accepted beyond almost anything were physicians and nurses. So what images were used to advertise cigarettes? Class, physicians and nurses. Here's one example. So they used doctors here. My favorite was doctors would be in regalia. They'd be looking over microscopes and they'd be smoking. So what you see, here's a doctor enjoying Lucky Strikes, smiling. The clear implication is he likes this brand. And this is the reason I'm showing this slide, other than just to take you down memory lane. Look at the statistic they gave you. They gave you 5 figures, 20,679. They didn't say 20,700. They give you 20,679 physicians say Luckies are less irritating. And then you can't read it, but they actually had a firm that did the accounting and whatever. And this was a form of statistical inference of the day, which we find amusing and a source of merriment and wonder. But I'm not so sure that comparable errors, if you will, or fallacies could not be repeated in another context. Obviously not this blatant and not this ludicrous. But it is possible to come up with other variations. So I'm using this as the prototype for people. I love this. Your throat protection against initiation, against cough, irritation against cough. So there's actually a website that has a lot of these, and they're really, it's very interesting. But statistics were used in this kind of unusual way to identify and induce individuals to take up a habit that obviously was an extreme health hazard. So then I present this. Now, Soren, if you have any questions, I'm not actually going to go into the problem here because I've learned that it will divert the entire talk. But let me just show you this. For those of you who believe that you can master any problem, if Soren hasn't already done so, he should present you what's called the Monty Hall problem. You've heard of this, no doubt. It's a game show. You make a few little assumptions, but basically, in brief, and I'm taking a certain number of liberties, the guest host will offer you the prize, or there's either goats or nothing behind the doors. And invariably, the Monty Hall omniscient actor will never actually, or at least I never have seen him, open the door if you win it correctly first time. So you have 3 doors, you pick a door which has the prize. It may be a car. They will never open the door that you've identified and say, you won, that's it, now go home. What they will do, as part of the game, is you pick a door, and then they will say, he will open another door. The other door being opened, presumably at random, is always empty. It will be a stupid game if he opened the door and just showed you. So, and then you are asked at that point, and assuming there's randomness to this process, you are then asked, should you switch or should you stand with your original selection? Now, I'll just tell you what the answer is, but please, if you don't agree with me, we'll let it go. The correct answer in the terms that I've just given you is that this actually is a specialized form of conditional probability. And no, the decision is not random. The decision whether to switch or not at the point and under the conditions I've just given you is a form of conditional probability, and you should switch. Now, at any one time, philosophically, you could say, what does it mean on one time that you have a higher probability of succeeding by one strategy or another? In one case, well, okay, but if you're going to play the game 100 times, if you adopted the strategy as I've just developed it, and you switch, and you had a bet going with somebody, you'd make more money. You all find this just understandable? Nobody is outraged and wants to tell me that it's can't be, that the odds have to be equal? You guys are good, because there are full professors of mathematics who get this wrong, who write letters objecting that this is the wrong answer, that you're an idiot, schools are failing. And usually people come up with a truly violent response to this. But anyway, the reason I'm doing this mainly to illustrate the notion that conditional probability is hard. You guys can get it, but a lot of people can't. It's hard. And many of the problems that we really deal with in medicine are modified forms of what I call a conditional probability. Soren may not. But to me, they're kind of conditional probability in that you have to understand certain premises, and then one premise actually conditions another. So I'm going to now describe the issues that we face with certain types of clinical trials. Not all, but certain types. Bear in mind, in my definition at least, genome-wide associations and functional genomics, in effect, are an example of case control studies, right? Very specialized example. Does anybody disagree with that? They're case control. You could not, in practical terms, in my opinion, design as an exploratory study a randomized trial where you're doing genome-wide associations on randomized patient populations, and then I personally don't think that would be, under some conditions, it might be practical. Almost all genome-wide association studies that I'm aware of effectively are case controls. You know what I mean by case control. I don't need to define that, right? Okay. So what we're going to talk about applies mainly to case control studies, of which genome-wide associations are part, but they apply for much knowledge. And some of these principles conceivably could also enter even into randomized trials, prospective randomized trials. So not all, but some of these. So I'm going to go over certain topics that I find especially burdensome in applying the knowledge, any scientific knowledge. Now, some of you probably know much of this already, and so I'll go fast. But there are several types of bias, and this is a short list that can enter, and they're fundamental, and they're really important to know. And they're not mutually exclusive. So one of the biggest bias features that you have is selection bias, which means you have differential access to a study population, or you have an unrepresentative nature of samples. And this can include biases that relate to self-selection and intuitively completely non-obvious things. For example, how many of you would find it intuitive, quickly, without doing a lot of thinking, if I were to say that if you have as your controls people who are at a job site and working routinely at a job site, fully working, active, and you were using some kind of endpoint, survival, mortality, susceptibility to disease, and you were taking as the control working individuals, that would introduce a selection bias. How many of you intuitively find that? How many of you would find that if I said that if you did that, you're actually going to buy a 20% artifact in survival, just on that fact alone? Probably. Could be more. Do you all find that intuitively obvious? You do? That's pretty good, because a lot of people in science don't. And they will use as a control for a certain population workers. There is a defined, well-established, well-validated, well-understood, well-characterized thing called the healthy worker effect, in which to my definition, it's a kind of selection bias. If you are actively working and you continuously work and you're showing up for work every day, you've already been eliminated from having certain illnesses, right? Because the sick people got selected out. So at any rate, if you're having a case control study, you have to know that fact and you'll be able to correct for it. But if you don't know that fact, and you'd be surprised how many studies are actually implemented that don't know that fact, you can run into issues. You can run into issues related to many issues parallel to that. There's something called a diagnostic or workup bias. That is, if you're developing a new diagnostic test and somehow, even in a subtle way that you're not aware, someone is using that diagnostic test to make a decision I'm studying whether a certain diagnosis or a diagnostic test can pick up appendicitis. And I use that test in some way that's not obvious as I'm performing it. And I use that to make a decision in real time as to whether I'm going to go in and do an exploratory laparotomy on people. And I don't realize what I'm doing. I may actually influence the test. And in effect, what you do in a complicated way, which we don't have to get into, you inflate the specificity of your test and you diminish the you inflate the sensitivity and you diminish the specificity of your test. You artificially inflate the sensitivity and you don't realize it. Okay, so because you're triggering the decision to go ahead, and therefore you're picking up more cases. But your specificity, you pay an enormous penalty on specificity when you do that, and a test must have both. Do you follow what I mean by sensitivity and specificity? If I wanted to say that one way to detect whether such and such a person test had a certain disease, if I had a test that was positive in everybody in the population, that would be a highly sensitive test, right? But it would be specificity would be garbage, right? Taking all comers gives you 100% specificity. You don't miss anything, right? Okay, but it's a useless test. Okay, all right. So that gives you these kind of issues. There could also be unrecognized differential attrition or participant dropout, or due to deaths or other things where you may not be tracking the records correctly. There's information or misclassification bias. You can have errors in the measurement of a key factor or outcome. You could have subject variation, observer variation. You could have a deficiency of the technology you use. You can have recall bias. This is a big problem when you are asking individuals to come in and remember whether something happened. You can have, and then that's a cause of something. You can have recall bias. You can have reporting bias. There are many different issues related to that. If you are doing a study whose subject is a certain condition association, and if it relies on people calling in to tell you that they're themselves have experienced something, you're going to get an unusual kind of statistical bias on that, right? Because the people that call in may not be the same thing as the population that you're trying to. They may have features about them that induce them to call in. So that's an issue. There are confounding biases, unfair comparison or distortion by some other factor. There can be phenotype suppression by unaccounted or unrecognized introduction of a therapy. If you're trying to study whether something is related to hypertension or not, whether something causes hypertension or not, but you don't recognize that something in your population is being administered to people to block their hypertension, and they don't have that phenotype, and you're not aware of that, your records aren't able to record that or capture that, or there's an irregular usage pattern, you can get errors in that dimension as well. My favorite when people are arguing with me on this point is if you had everybody was on a diet that had extremely low phenylalanine in it. Everybody was on such a diet. Then you would not have picked up the gene for phenylketonuria. You would not recognize it as an illness. Probably, right? Or it would be. You see the point I'm making. If you, in biology, they call that the notion of an auxotrophic mutant, right? Where you essentially you correct the problem and you, in effect, provide the conditioned media that can actually correct the problem. So basically, I want to talk about stage migration. This is another thing, particularly in cancer. Now, remember I asked you earlier on to remember the picture with the guy that was on the extreme left? So now I'm going to illustrate the problem. If the guy that was on the extreme left, the guy that was sort of poking into the camera trying to get himself in the picture, had been asked to leave the picture before the picture was taken, and the remaining three people, Gene Myers and Ham Smith and Craig Venter, were remaining, you would see by that exiting, you would see the average IQ would go up. Right? If you understand that feature, then you understand the fundamentals of stage migration. Now, I will illustrate stage migration. My experience when I give these talks is that people always, not always, but frequently say, this is so obvious, why are you bothering me with this? And I'm bothering you with this in part because this is a mistake that is made over and over and over again. and almost has the same pattern. Someone forgets this concept, writes a paper about it, and then there's a series of comments and letters to the editor pointing out that the person forgot this notion. So maybe that era is over, but I don't think so. Do you know what I mean by the concept of stage migration? It is called the Will Rogers effect, but I will not repeat why because it's politically incorrect for me to give you all the different reasons. But Will Rogers was one of the comedic American figures who first described this phenomenon. He was not a physician, but he essentially captured what this is. What it really basically boils down to is, let's say you have, I'm going to make it simple because cancer usually is not divided this way, but let's say you have local disease and advanced disease. Just two categories. Usually it's not only two categories, but for instance, local disease and advanced disease, as defined by a certain technology of the time. Supposing you then come up with a brand new technology, an imaging technology, that is able to see tiny, tiny bits of tumors that have actually spread, thereby rendering the patient advanced. It's no longer at the local site anymore. It's advanced. That's what I mean by advanced. Metastatic. It's gone to another site. But you're now using a new technique. And it shows certain people that previously would have been thought as having local disease only. What will that do to the apparent survival features of the people who previously would have been categorized as local disease? What would that do to the new category of local disease, those new people classified the new way? What does it do to their life expectancy? It improves it. What does it do now that you are reclassifying those people and you're putting them into the more advanced group? What does it do to that group? Speak it. Pardon? Yes, precisely right. You now have a phenomenon in which you have actually improved both groups, right? But accomplished nothing. You can't cure cancer by fiddling with numbers. What you are doing, at least the cancer cell is unimpressed, although people have tried to cure cancer that way, it never works. The cancer does not care if you are making statistical biases or not. It will keep growing and keep injuring people. So what we actually have is a phenomenon in which a new technology, by redefining something, by restaging people, if you want to look at it that way, now creates an artifact, if you're not careful, of effectively seeming to improve people that have local disease only, purely local, and also because the new population of advanced disease, but they're really better than the old style advanced. They come into the new category and they dilute out the previous badness of the disease. So both compartments now got better, right? But nobody got better. To me, Soren may disagree. This is a kind of specialized regression to the mean kind of thing. You're just diluting everything out. You're not changing anything. You're changing the mix, but so you're creating more of an average between the two without realizing it. That's my way of looking at it, not as a statistician, but that's so you do not change the median survival of the population as a whole, and you will not, by having that maneuver, do anything to the public health statistics of how many people die per unit 100,000 in an age-adjusted way. You won't do a thing. Death rate will be the same. And then people say, well, how can it be? I had a neighbor that had lung cancer, and they found that it had spread to X, Y, or Z, and they lived 10 years. Well, yes, but it wasn't the same thing. And there's a related phenomenon called, and we have to discuss this, called lead time bias, which is related in a broad way to what we're talking about today, which is if you develop a brand new technology and it can detect a cancer, even a primary cancer, much, much earlier than a prior technology, from the point of your detection, you will think that the person has lived a long time. So, for example, if you say that people with lung cancer may live only 2 or 3 years, let's just make up that statistic. If you have some new way that diagnoses them way, way, way earlier than you ever did before, you may say those people, they're living for 10 years. Well, not really. You've just set the clock back 8 years. You have done a thing. You've just discovered it in an earlier phase. So these are concepts that I think you have to keep in mind. And what do they end up doing? They end up making it much more difficult to come up with an evidence-based conclusion And they force you sometimes into the domain of having to do randomized prospective trials, which are now and have been the gold standard. But randomized trials, important though they are slow. And you can come up with any metaphor you want, but it's, in my way of looking at it, almost like I've invented the internet. I'm going to send an email from San Francisco to Providence. Doesn't quite go at the speed of light because of all the changes in servers and everything, but it goes pretty fast. So let's say a few milliseconds, a second, whatever it takes, assuming the servers are all working. Well, okay, then my technology involves that I have to get on a train and ship the message by hand to Boston, and then I have to put on a steamship and take it to Europe, the ultimate destination for my message. Now that may be unfair, but those are the time scales not that off. Basically, the process of doing randomized trials, yes, there are improvements, there are technical improvements, there's this and that, but if it takes 5 or 10 years to understand an answer, it's going to take 5 or 10 years, and you can't shorten that part of the equation with randomized trials. So they're the gold standard, but they're very difficult in the processes. So they do certainly apply, many of these concepts certainly do apply to genome-wide associations. Everybody recognizes you can have false positive results and selective reporting of these issues. So type 1 errors are particularly relevant to the conduct of genome-wide associations. When you're searching hundreds of thousands of genetic variants, you always have issues that could be by chance. You can find false positive results. You can do your Bonferroni corrections or whatever, but still you can get into issues. And because at the end of the day, a genome-wide association study is a case control study. And all of the biases that I told you and more that can perturb a case control study can perturb a genome-wide association study. So those are certain issues that we have to deal with. Then there's a different and evolving knowledge. Now, much of what I'm going to talk about today is related to, I'm going to focus on prostate cancer. But some of these, in a variable way, will apply to other cancers. So let me focus on prostate cancer. First, let us define our terms. As a practicable, none of the people in this room who carry 2 X chromosomes need fear it. Those of you who carry only 1 X, and by implication a Y, may get it at some point in your life. It's a male disease. Prostate cancer occurs. There has been a huge effort to develop early screening technologies to catch prostate cancer when it's early, and in that capacity potentially prevent deaths from prostate cancer. So, how many of you like the notion that catching a tumor early is a good thing? Do you not trust me? Would I ask you trick questions? So, yes and no. Here's where my definition of conditional probability comes in. Soren will not probably like this way, but it's my, remember, I'm a doctor, not a statistician. I can say or do anything I want, really. Statisticians will clean up my mess. It's a kind of conditional probability in the sense that it all depends on what you believe and what exists as the predicate for the screening. So let's walk through this. I'm focusing on prostate cancer. The caveat that I give you is some of what I'm going to say may or may not apply to other cancers. On the other hand, they might. And they will therefore allow you a framework for asking relevant questions, which will perhaps allow a more intelligent debate. The notion that catching tumors early is a good thing is very well established, and it's true in some senses of the term. It is true you would like to catch a cancer early. But certain implications of that philosophy, if left unexamined, lead to frustration and endless debates. What we have to this day is an enormous debate about whether PSA screening, prostate-specific antigen screening, is going to translate as a public health benefit to men. Okay? Now, when I go to the doctor once a year, I get a PSA. They check it. The men in this room are too young, but someday, probably by the time you hit 50, somebody's going to start asking you about PSA. And I'm not in any way saying you shouldn't get a PSA test. But what we have as a screening test, you know what I mean by a screening test? You know the difference between a screening test and a diagnostic test? Although the distinction is sometimes blurred. A screening test is performed on a perfectly well individual without any clinical provocation other than certain demographics, maybe age or something. You don't. If you're getting a test because somebody's sick or is complaining of something, and then you're starting to work up that person as part of the test, it's not a screening test. Okay, it's a diagnostic. So a screening test is something that, I use the term, is done unprovoked. You come in, you get it, that's it. What has happened is that there has been this endless debate about whether PSA screening really has been able to reduce the death rate from prostate cancer in this country or else other places where it's been tried. And the answer is there's more heat than light being generated on this topic. And many people quite fervently feel that PSA testing has not had caused a drop of the death rate. Others feel that it has benefits. And I'm not going to get into that debate with you. I'm going to let you define your own definition. But let me tell you some of the parameters that make this much more complicated and make the notion that yes, it's a good thing to catch cancers early. And the point I'm raising here, it depends. It all depends. It is, in my definition, a form of conditional probability. All right, so supposing we have a cancer. Let's focus on prostate cancer for a moment, because these things actually may have some relevance. And we're talking about cancer can be microscopic, localized to an organ, regional spread, and metastatic spread. Okay, cancer progression on the ordinate. On the abscissa is time. All right, so let's do the next slide. Let's examine tumor A and tumor B. First, tumor A. Tumor A remains undetectable and without morbidity during the patient's lifetime. Okay. And that, by the way, is my personal definition of something that's indolent. It will not bother you during your expected lifetime. This is not to theoretically project that if you had lived, if your expected life expectancy is 80, if you had made it to 150, it would have showed up. That's not what we're talking about. We're talking about you're living a normal life, and before a competing cause of death supervenes, this thing causes a problem. Okay? Do we all agree with that definition? Okay, so this is the tumor remains undetectable and without morbidity during the patient's lifetime. In other words, yes, you see a tumor there. It's little nests of tumor. It hasn't invaded. Invasion is quite critical. It's in situ, so to speak. It's there. And you can find lots of those in post-mortem examinations of men when you look at their prostates. Little nests of tumor, they're not going anywhere. They don't appear to do anything. Would screening be very useful in this category? No. Could it cause harm? Yes. Not just economic harm, because you might need to do an invasion or some kind of quasi-invasive procedure, or, we'll talk about this in a minute, there may be certain operative procedures that follow. Tumor B. Tumor B grows until it becomes detectable, but never really causes symptoms or leads to death. In other words, it's there, the PSA might be bumping up. Is this likely to be benefited by screening? Is it possible that it could cause harm if you had a screening program? Okay, because this category of tumor might be the very one where somebody says, okay, I need to do a radical prostatectomy, or I need to use early radiation on you, or I need to do the robotic surgery that people are doing now. What are the complications of that? Well, some men will get incontinent, some men will get impotent, and yes, there will be bleeding and other effects. Maybe those are small, maybe they're dependent on the surgeon, but it isn't entirely fair to say that what's the harm of making an early diagnosis. So this is a reality that occurs, and if your disease is predominating in a population under screening, if this category of patient will be a high percentage of what you find, what will it look like on your cancer statistics? Will you have an effect on the cancer incidence? Yes, you will. You will have a surge in incidence at the time the technology is introduced. Will you have an effect on death due to the disease? You'll have an effect on death? I would vote no. I would vote that you won't pick this up on a population-based thing because these are not tumors that would have declared themselves necessarily but for the screening. They're not going to kill you, right, as a cause of death. Does everybody go with me on this? Because I'm not going on to the next slide until I have an absolute unanimous consensus.
They'll change. It'll look like more people are surviving.
It may look that way. It will certainly look like you have an epidemic of the disease. You will certainly get notice of people saying, my God, we're having all this prostate cancer showing up. Right? But you won't see a difference in the death rate. The death rate is not subject except for recording errors or diagnostic errors, which are not realistic here, because death rates are recorded by death certificates. And within large measure, every death in the United States is recorded in the National Center for Health Statistics, and there's pretty good integrity on that. And so if somebody writes down the death certificate, died from prostate cancer, the odds are they died of prostate cancer. And that kind of, even if they're having a systematic error, even if you have a doctor somewhere who's crazed and won't write that down, that's going to be a systematic error probably. It's not going to give you an artifact in the usual sense. So death rate is really a rock-solid statistic. It's called age-adjusted death rate. You understand what I mean by age-adjusted? I'll take your silence as a no. Okay, age adjustment is a statistical tool that needs to be done whenever crude statistics are introduced. And what you do is you essentially, for want of a better term, you normalize or standardize. It's analogous but not literally the same thing as grading on a curve. Do they grade on a curve at Brown?
Yes.
Boy, it must be some tough curve. Okay. It would be analogous to having a pool of institutions and grading on a curve but not correcting for how many Brown students there were. Okay? So let me go with that. If you don't know that a population has changed in age and a tumor is related to age, which it is, but you don't know the population is aged, if you have certain raw figures come in, you're going to say, well, we have an epidemic of cancer. Well, really, it's not that at all. It's that you didn't realize the population had shifted, if you see what I'm saying. So what this is, for want of a better term, a way of normalizing to a given standard population. Usually you normalize to a 2,000-year population. It's called age adjustment. If somebody, and this probably won't happen, but in the odd event that somebody does a presentation and you pick up the notation that they're not age adjusting their statistics, you can stand up if you're in a bad mood and ask them if they age adjusted, and if they didn't, they've committed a serious thing. It's analogous, but not homologous, to failing to report something in constant dollars if you want to know if something was more expensive in 1910 versus 2009. Are you with me? It would be hard for you to know if something is more expensive or not unless it was reported in constant dollars against some standard. In brief, that's not correct literally, but it's spiritually correct. So you need to have age-adjusted statistics. So basically, we have not seen a dramatic drop in the age-adjusted prostate cancer rate in this country. We see about, same number, roughly. There's been massive screening programs. So I think those are, maybe there's been a little trend down, but really certainly not dramatic. And that has introduced issues for people. And there are also controversies when randomized trials have been done. It's been difficult to show a survival advantage. I'm not saying there aren't some studies that might, but there's always complications in this field. At any rate, my main point is that you need to segment in your minds how a profile of a cancer looks within these parameters. This is work by Esserman and her co-workers in San Francisco, and I thought was unusually clear, and that's why I'm parroting it. Okay, so the point here is both tumors A and B represent low-risk indolent or indolent lesions of epithelial origin. They're tumors that are indolent. They can be there. They're probably not going to contribute to death. And therefore, screening is not likely to do you a lot of good if a lot of the patients in your tumor pool are in this category.
So the question about this, it seems like at least I mean, it seems like the fundamental problem here is that the probabilistic interpretation of the test isn't really being respected by the policies that are being instituted, right? Like it seems like it wouldn't necessarily be an issue to do early test PSA screening if everyone accepted and understood that this means, you know, your conditional probability of getting tumor A could possibly be quite high. You know, and it seems like the problem comes when you're instituting policies that previously existed for maybe diagnostic tests, right? So that, and then you're applying those same policies to what's really just what's really not. You know.
I think that is a brilliant and utopian point of view. It is true. What you said is 100% correct and insightful. But I think that in the practical reality of something, it is very difficult to ask a patient to come in for an annual test, get it, giving what you've described as essentially a statistical informed consent. I'm going to explain to you, I'm doing a test, and these are some issues that we're going to talk about. These are the limitations of the test. It is very difficult then when you get a positive result not to act on it. So for the one person who is declared to become a physician, you're going to encounter another phenomenon. Many of you are going to be doctors. You just don't know it yet. So you're going to encounter another thing. Somewhere along your career, I promise you, you're going to be in the following situation. You will either have ordered a test or will be in the room when you ask somebody who orders a test, why did you order the test? If the test apparently had no relationship to what you're worrying about on the wards at the time, and the test is way off the categorization of what you thought you were working up and dreadfully comes back positive. Okay? I promise you you're going to be in that situation. And basically what happens is somebody is on the wards for a pneumonia and somebody gets a test that has nothing to do with pneumonia, nothing to do with the patient, and it comes back positive. And now what? Now you're going to have to work it up. It doesn't matter how it got there. And that's a real phenomenon. For example, we now are seeing imaging companies that have these little vans that come around. They'll do a total body imaging for you. They'll image you from head to toe, and they'll find early lesions. Guess what? They'll find something that you didn't know you had, a lipoma of the spine, a little thing here or there, whatever it is, and guess what? You're going to have to work it up. Now, you probably cannot ignore it. Probably. For many reasons, including human nature, but there may be other reasons as well. So it is very difficult for me to envision a paradigm of screening, public health screening, in which you, in effect, screen the patient, but give a number of statistical caveats. That would be true if this were Plato's world and both patient and doctor were philosopher kings, and you were then able to have a learned discussion about that. But I will tell you that when you are a patient, no one is a philosopher king. I don't care if you're a Nobel Prize winner. If a doctor says you might have cancer, then all the stuff that Woody Allen used to have in his movies, all is true. You hear the word you might have cancer, that is a life-altering experience. It is not something you can say, well, I can statistically worry about this, and I'm a Bayesian, and whatever. It doesn't work that way. So, please, you disagree with my interpretation? Pardon?
I don't know.
No, there's somebody be.
Oh, we actually do that for aneuploidy screening for unborn children. They get a quad test, they get an alpha-fetoprotein, an estriol, avidin, etc., and they're not given a yes/no answer. They're given an age-adjusted risk of the chance of having a child with aneuploidy, which is trisomy 21, trisomy 18. So you're not told yes or no. You're told 1 in 200, 1 in 600, 1 in 35, 1 in 50.
Yes, indeed. I like that analogy. It's a good counter. But what I would want to just rebut or give you my riposte is, I would venture to say that on a statistical basis, what you've described has a lot more sensitivity and specificity than PSA screening, even with the caveats. And so I would, not having studied the matter, I would say that yes, you do have those corrections, demographic corrections, but even with those corrections, the inherent validity of what you're offering is much stronger. Because it is this mix, but I could be wrong. So it may well be that you're doing that. But this mix is really what determines the public health value of whether you're going to essentially say everyone over the age of 50, every male over the age of 50 is going to get a PSA. That's everybody, and that introduces special issues. Yes, you may be able to find examples where it works. I'm not sure that it could be applied as quite so easily in prostate cancer screening, but we could have a discussion. It's certainly open. Now, tumor C is destined to become metastatic. That is essentially the surrogate definition of fatal. If there are some exceptions to what I'm going to tell you, and yes, certain primary tumors, depending on their position and so on, can be lethal and all right, but usually when you're talking about a cancer death, usually you're talking about a cancer that has become metastatic. It has gone from its primary site. That's typically what we're talking about. There are some exceptions, but that's typically. So tumor C is destined to become metastatic and fatal, but can still be detected while still curable. That is surgically removable. Will this category be benefited by PSA screening in prostate cancer? Yes. This is it. This is the Holy Grail. This is what you want. You want this particular group. If this were everybody were like this, this would be the group. Then you would have screening would be relevant. Okay. Now, tumor D is destined to become metastatic, but it grows so quickly that by the time it's detected, it may no longer be curable. Is this likely to be benefited by screening?
Yes, if it leads to lower medical costs of future screening. I mean, it seems like quite reasonable if you know it early. At least you know what you're getting into.
That is not a phone call. That is my timer. Okay, so it's a very interesting point of view. It is not the classical point of view for screening, though, because the way this has been set up is that the tumor, by the time you detect it by your whatever technology, it has already crossed some Rubicon within the patient, and it is immutable what you're going to do, if you see what I'm saying. So yes, you could create scenarios where you do want to know. You could argue that it is always better to know. A person needs to know their fate. You could argue that there may be certain additional benefits, but at least from the showing, if you're arguing the benefit must be reflected in the drop in death rate, then probably this wouldn't work. Let me give you a tumor where we do not have debate. Cervical cancer. I doubt if you're going to find very many articles in the literature that argue that cervical cancer screening, as we do it now, which is either pap smears or DNA capture, or whatever you want. Cervical cancer, as HPV-associated cervical cancer, human papillomavirus associated. I doubt if you're going to find a lot of articles saying, it's just not effective, blah, blah, blah. You won't see very many of those because there isn't any debate on that, practically speaking. We know, and that's reflected in the population statistics, and you can make all sorts of correlations. Screen women, despite the potentials for artifacts that I've described for you, screen women virtually always have a lower death rate than cervical cancer. You can see in the national population statistics that cervical cancer is dropping, no doubt related to those kinds of interventions. So there's a classical example where you just don't have the debate. You're catching the cancer early, you snip it out or do whatever you wish to do, and that's it. The woman will not die of her disease. You can always get into a philosophical question about whether you're intervening on a certain number of women who won't benefit. Their tumor wouldn't go on anywhere either. But there is no question that you're getting a benefit, and the kind of intervention you're doing is relatively cost effective. Another thing which is not quite as dramatic and not quite as solid, but still pretty solid in most people's views, is colonoscopy to remove polyps. Yes, you're going to remove a lot more polyps than will become malignant, but most people sort of no longer consider colonoscopy that invasive, and hey, you feel good with the propofol and whatever, and you get the screening, and the polyp is removed, and the person will not have a polyp that has a potential to become malignant. And it's in a relatively accessible position. There's usually not much in the way of untoward action. So I'm not saying that that's quite at the same gold standard level, but it's still pretty high. But for prostate cancer, and by the way, we are seeing colon cancer statistics drop for many reasons in this country, so it all fitting together in some manner or means. other screening approaches, even hemoccult might be doing something. But in prostate cancer, it's this mix, or any tumor, it's really this mix, right? And if you don't know the mix, you can't be sure what your screening is going to do. So there have been suggestions. Oh, by the way, I want to introduce one other concept for you to think about. Do you know what the concept of an interval tumor is? So supposing I have a screening schedule, and I'm screening somebody. In this case, I'm going to include breast cancer for a moment to make a point. I'm going to do PSA screening, and I'm going to do mammography, okay? Let's say I do mammography, some people like every year. Let's say, though, I'm going to do every 2 years, okay? If I pick up a tumor on the scheduled annual or biennial date, is that likely to be more or less lethal than a tumor that comes in to the woman, discovers it during the interval, and reports it to the doctor, it not having been seen in the previous test? Assuming in this discussion that we're not talking about technical errors, the radiologist didn't miss it or anything, no technical errors. Now that's what I mean by an interval. The thing popped up clinically between normal screening times. And the patient is now coming in between screening times, and by definition, if a patient comes in with a problem, it's no longer screening, whatever your definition. Even in my opinion, if the patient comes in and says, "Doc, I'm just not feeling well," if you do tests at that point, I do not believe it's screening. You can have intuition, you can have other things, but it's not screening as some doctors might not quibble with me. They'd argue with me. They'd be wrong, but they would argue with me. Maybe I'm wrong. But you see, now which is the tumor? Which is likely to be the serious, more serious situation? Pardon?
The one between screening.
Exactly. Now you now know a fact that many doctors don't know. So interval tumors typically, classically, are more to be feared unless there's some error. Why? Because they have a certain growth velocity that they've declared. They weren't there the last time you checked. So statistically, there may be some serious growing going on. There may be a serious velocity going on here. And those, more or less, are not good tumors. Whereas if you're picking up something in a regular schedule, well, then the statistics might favor that it's growing at a more mannerly pace. Okay, so if you're going to screen, in my opinion, and many other people believe, this is the group you've got to have, and the proportionality of that group is going to determine the effectiveness of your screening. So while I'm deliberately being agnostic with you about whether PSA screening is worth it or not, I am introducing that just because you're catching small tumors, and my God, it's got to be good to catch a small tumor, is not always correct. I have had very high-ranking people in the oncology community, high-grade authorities, tell me that I was an idiot, which I said may be true, but nevertheless, small tumors do not always kill you. So that is the issue. The point is that we can't be trapped in our own discussion from first principles. You can't just assume that a small tumor, it has to be susceptible to a benefit by being removed early. It may be true, but it may not be true. You may be causing a diagnosis of cancer. And what is that called, by the way? That's called overdiagnosis. That's another kind of statistical error. Overdiagnosis, which in my opinion is defined by the term of identifying a tumor that otherwise would have been benign and not cause problems for that patient during his or her lifetime. And if you diagnose a cancer in that context and say it requires an evaluation that otherwise wouldn't have required, then you could be open to something related to a statistical artifact called overdiagnosis. Now, why is this important? This isn't important to make a point or to get into debates. It's important because many times we have public health policies and we're disappointed when they don't work. Okay? And so we need to think about it this way. It also is a warning about how there is not necessarily linearity in making discoveries from the genome, making something that could be a biomarker or whatever, and so on. So this is causing people to rethink. This is an article, I urge you to look at it, from Estimate et al. And JAMA, just came out, 2009, volume 302. And basically, you're talking about additional costs. You're talking about a number of issues to the healthcare system. But it could also be, some of what I'm talking about, though not all, applies to breast cancer. I will say that mammography, particularly in certain age groups, clearly has a benefit and has been shown to reduce deaths. That does not mean, however, that some of these issues do not apply to it. So this is another issue, probability of death from breast cancer compared with death from other causes at a time interval from breast cancer diagnosis. So this is another way of looking at the problem. Even if a woman has breast cancer, if she is caught very, very early, her lymph nodes are negative, it's very, very early, it does not mean she will not die of breast cancer and that the diagnosis was in vain. It certainly will, she may die of breast cancer, it's certainly an issue, and it was good to do the operation in this context. But other causes of death shown in yellow can still predominate. This is if she already has early breast cancer. She may face a higher death rate from a competing cause of death. Heart disease, stroke, certain other conditions, certain other tumors. So this is a reason to individualize, in my opinion. We need to treat the entire woman in this context. Human beings are not simply the sum of their organ parts. And even if someone has early cancer, it still might be important from a statistical point of view to assess what their risk profile is for the diseases that they face, not just the cancer or the problem that's in front of a particular doctor. And this is a reminder of that. So, another slide to show drug discovery and development. This is a slide put out by the industry, pharma. I'm merely copying it, but I think it's probably correct. And this shows you the timelines that it takes to develop a drug. And you want to add these up, it could take about 15 years to develop a drug from the identification of a compound. Yes, sometimes things go faster, and I'll even show you some examples where it can go faster. But my only point here is that it takes 15 years. If the genome gives you a clue, there's no guarantee that it'll give you a drug. I've yet to see a genome-wide association study that shows this is linked to a disease. Oh, by the way, the genome-wide association study has identified a new drug that will work in this context at the same time. It doesn't work that way. It's an invitation to begin research. Important invitation, but it's still an invitation. So you still have these timelines. So this is another answer that somebody's going to come up to you at a cocktail party and say, why does it take so long to develop drugs? And you will say to them, why are you asking me? And I promise you, they will not stop. So this is the phenomenon. Hurry up and wait. We have the human genome, we have genome-wide associations, but then you're back to an old paradigm. You're back to the paradigm of how do I develop new diagnostics, how to do the clinical trials. Those are not moving any faster yet. This is one exception to this. Now, this is the death rate due to HIV/AIDS. Age-adjusted death rate in the population. Do you notice anything unusual about this curve? I love this curve. I find myself looking at it longingly. This shows something that's basically unprecedented. It shows that the death rate of a disease, a major disease, this was the major killer of young people, ages up to 44 for in the year 95, 96. It shows that, but this is the total population, the death rate has dramatically fallen without an effect on incidence. The epidemic did not stop. There was not an effective vaccine. There was not a sudden cessation of transmission. This is unprecedented, as far as I know, for a lethal chronic virus to have its death rate precipitously fall absent some dramatic paradigm shift, such as a vaccine or some incredibly effective prevention. So this happened. Now, there's another issue here. If you had been a planner for years 87 through and including 95, or let's make it 94 from simplicity, you might have concluded, if you were Bayesian, that further addition of money into this field, this is antiretroviral therapy, would have been futile. Right? The curve is going up. You're having all this research done. Year after year, it's going up. Maybe you call it, throw the towel in, right? Okay. So anyway, I'm introducing this because I really love this curve. You don't get to see curves like this too often. I'm not saying you never get to see them, but you don't get to see curves like this too often. The death rate in adults has dropped. Maternal fetal transmission, in this country at least, has dropped very significantly. It is possible in children to restore growth velocity and even to reverse certain forms of dementia with certain antiviral drugs. So it's a very interesting and gratifying example. And this, again, is to show you, in this case, I'm not showing the total population, 25 to 44-year-olds, you'll see that about 94, 95, AIDS was the #1 cause of death in this age group. You'll also see as an internal control that for practical purposes, there isn't some statistical weirdness going on. You're not the other causes of death, cancer, heart disease, suicide, homicide, chronic liver disease, and so on in this age group did not suddenly have a disappear or whatever. It's selective for individuals. Now, what happened in this year, 95? What happened is highly active combinatorial antiretroviral drugs finally came together, were implemented, and within a year, the death rate started to drop. I'm just showing you this because this was my lab's first work with AZT, which is one of the components. There's the structure. We showed that AZT actually had activity in a laboratory setting and submitted this paper in June of '85. Please, if you would remember that date, June of '85. The drug itself, we had the clinical trial, the phase 1 clinical trial reported by March of '86, and the drug was approved in March of '87. So that's a real outlier for what I showed you for the 15 years. So under some confluence of events, you actually can move pretty fast. The other thing I would say is this was before the genome, and this is before we even had PCR. We had no molecular diagnostics. So this was really an ancient time. We communicated by phone. Fax machines were still relatively novel. I'm not making this up. You know, basically, if you want to do a paper, you had to sit down in a Selectric, and God forbid somebody made you make suggested changes, because it meant, I mean, there were no PowerPoints. If I were doing this talk, I would do glass slides or Kodachromes or whatever. Okay, so why did this work? What is this? Is this a positive example? What happened here? Well, for one thing, there are a lot of factors. I won't cover them all, but one key factor was the development and acceptance of reliable surrogate markers. Viral RNA by RT-PCR, by polymerase chain reaction, became a surrogate marker, became accepted, and it became possible to develop new drugs or drug combinations and see very quickly if you're making progress or not. And therefore, if you weren't, you could abandon a regimen, deselect, as they say, euthanize the drug, and go on to other drugs. But you also could approve the drug quickly if it had surrogate markers related to viral RNA. You could begin a kind of conditional approval by the Food and Drug Administration, what they call accelerated approval or Subpart H approval, which would mean, yes, the drug can be marketed. You'll have to come in with your clinical endpoints later, but in the meantime, people can reliably depend on an experimental drug, and it can be marketed and released and available. So I think this changed everything in both adult and pediatric. When we were on our pediatric wards, we collaborated with Phil Pizzo, and we had results in children that were literally unbelievable, even to colleagues. We watched children have reversal of what was being called cerebral atrophy. We watched increases in IQ. We watched increases in growth velocity. And we had colleagues who literally and specifically told me they did not believe the results because such results were impossible. So there are ways in which you can get around the paradigm. So now I want to talk about, very briefly, viral load testing. Surrogate marker was able to accelerate everything along this pathway, but in particular new drug development. You had a very rapid cycle. You did not have to wait for clinical endpoints. The first randomized trial with AZT used death as an endpoint. Placebo-controlled trial. I guarantee you don't want to do that more than once. Very, very difficult to do. All sorts of ethical issues, many different issues, but I believe to this day, however, that had a placebo-controlled trial not been done, it would have been possible to achieve a consensus that AZT was working. Every one of the artifacts that I was telling you about would have been invoked. A placebo-controlled trial does not end all of that, but it markedly, if it's properly conducted, it markedly reduces many of the kinds of artifacts and selection biases that we talked about. Okay, let me talk about surrogate markers and what I mean, so that those of you in this room with your formidable intellects will solve this problem, because I cannot. The problem is this. We have different definitions of surrogate markers. Is it an endpoint measured in lieu of some other so-called true clinical endpoint? That's one definition. An observed variable that relates in some way to the variable of primary interest, which cannot be observed directly. That's another definition. But this is my favorite, and this is, I think, the operational definition. A surrogate marker is a response variable for which a test of the null hypothesis of a relationship to the treatment groups under comparison is also a valid test of the corresponding null hypothesis based on the true, almost always clinical, endpoint. So in other words, a surrogate marker can be used, and it will give you the same answer rejecting the null hypothesis. You know what I mean by that, right? That's clinical trial is said to be positive in favor of arm B versus A, or the other way around, if it rejects the null hypothesis. That is, the two cannot be assumed to be the same. It rejects that with whatever confidence intervals and whatever p-value you choose to select. So and usually the p-value is 0.05, but if a surrogate marker can obey that principle and conform to that, then it's a surrogate marker in my view. This is the so-called Prentice definition. Not everybody accepts that, but I think it's the most useful. 3 attributes of an ideal surrogate marker. Surrogate marker must be prognostic for the disease or disease progression. The surrogate should be affected by treatment if you're talking about treatment research. And the effect of treatment on the surrogate should mediate the effects of the treatment on the true endpoint. That's what we need. That's what I hope the computational biology will identify for us. Novel hints of what is a true surrogate marker. Issues to consider: a prognostic marker or factor is not necessarily a surrogate marker. Is that intuitively obvious? Something can be prognostic, but it isn't a surrogate for how a drug works. Okay? Validating the mechanism does not always imply a good surrogate status. That is, effects on the expression of a putative marker may not necessarily translate to effects on survival, disease progression, or related clinical endpoints. And a positive result in an early trial on a putative surrogate marker does not automatically imply that one has a truly validated surrogate. So those are all pretty obvious. And then I leave you with this. This is a slide that I like. So this is a slide which I label "Think Outside the Box." And don't let first impressions fool you. So basically, you have these settlers marveling at the stupidity of the people protecting their homes about to light the burning arrows at them. What an idiotic thing to do. And then they realize they're doomed. So I think that's an important lesson for all of you, and I hope that this has been a good dialogue and conversation. Thank you.
Any question? So, do you think that pharma knows what they are doing? I mean, in the sense that you see their chaotic move in which there are, I don't know how many compounds distributed per teams. Every team gets like a bonus if they can go to the next level. It's not clear that they have any strategy other than, maybe randomly they are going to guess something. What is your critical view of what's going on inside drug design?
I think this gets back at the tools that are available for pharma. And I'm not sure pharma or other sources currently have all the tools they need to develop drugs for exceptionally difficult diseases. I think we can expect pharma to do a good job, probably, in coming up with new generations of drugs to treat high blood pressure or things along those lines. I think in some cases pharma can act pretty quickly. I think they did act pretty quickly in HIV-1. And particularly, they were able to act with great speed and effectiveness once it was clear that they had a reliable surrogate marker. I can't emphasize that enough. Now, I would love to tell you, in an act of self-glorification, that, we developed AZT and several other drugs, and actually they went to NDA status, new drug application status. They were approved without any molecular diagnostics, without anything really to speak of. It can be done. But it's warning, professional stunt drivers, do not try this at home. You can't have an industry based on that. You have to have, for pharmas, they have to have some reasonable road to approval. For pharmas, everything depends on whether a drug will be approved by the relevant health ministry. In the US, it's the FDA. They can't afford to be interested in a product that has no, or a pathway that has no likelihood of going to an FDA approval, right? They don't earn any money unless they have a drug that can be shipped in interstate commerce and promoted. That requires FDA approval. And so they needed, and they got with HIV, because the original preposition and proposition for AIDS was that pharma would not respond, that the problem was too intractable, and they would not make a commitment. One or two companies, or very few companies, were an exception. Burroughs Wellcome was one exception, and I work with Burroughs Wellcome and AZT. But by and large, once it became clear that you had a surrogate marker, a reliable surrogate marker, that would be a pathway to approval, it made it possible to really have lots of companies come in. It made it possible to examine combinations and instantly add or subtract. It made it possible to detect resistance and to develop profiles of drug resistance, including sequence-based methodologies for identifying drug resistance in the reverse transcriptase or the polymerase gene, the protease gene. And basically, it made it a totally different developmental program for them. They did not have to use death or advanced disease as an endpoint, and it made it possible to develop lots of things quickly. And that, I think, led to the drop in death rate. We don't have that in many diseases, however. We actually have to do clinical endpoints, and that almost by definition means very large clinical trials with rare exceptions, with some exceptions perhaps in certain fields, but by and large, you need large clinical trials, which are expensive and risky. And if the drug fails, you don't know why it failed necessarily. And if it succeeds, you don't necessarily know how to come in with an improvement. So I think those are real issues. Pharmas should write you an enormous unconditional grant and should allow you to apply new tools of computational biology, computational genomics, to begin a search for reliable surrogate markers in the totality of what that means. Now, it doesn't necessarily mean a blood marker, but something, a test, a profile, a diagnostic, something that allows you to predict what the null hypothesis test is going to yield without having to wait for the clinical endpoint. And once you have that, you can drop an enormous amount of time off the development program. You can drop costs and so on. So the answer is pharma has a significant challenge, and I don't know precisely the pathways that one would need to get them to adopt other paradigms. Also, you're going to have the health ministries. You're going to have FDA on board on this. They don't like surrogate markers. They will use them under some conditions, but they don't like them because they have been burned, in all fairness to them. They don't even like pure studies based only on hemoglobin A1C for diabetes, which is a pretty good surrogate marker for glucose control, without integrating other things, including overall health effects and so on. So I think that those are real issues, and I think in cancer in particular, yes, we sort of have surrogate markers, but sometimes we think we have a surrogate marker. Some people think tumor shrinkage can be used as a surrogate marker, and it can, no question, in some conditions. But there are times when tumor shrinkage doesn't translate to overall survival. And then you have a problem. So those are issues.
Soren, in response to your question about pharma, I'd say they're both friend and enemy. Friend done some spectacular things. AZT, AVEC, other things come straight out of the lab, spectacular success. Where they're bad is drugs that have marginal differences, over-manufactured, over-pushed, over-studied, wasteful, small, incremental, minimal improvements. So for new things like HDAC inhibitors and stuff, they're going to be invaluable. But then there's going to be a whole rash of HDAC inhibitors that are going to get pushed, and that's adds to the cost. So friend and enemy.
No doubt that they are making great contribution. The point is if they have a strategy other than randomly trying things or buying companies for which the small company discovered the drug.
Well, let's be honest. Some pharmas will do that as a strategy. Some pharmas have enormous capital reserves, and their strategy can be, I will allow a smaller biotech company to get to a certain point. I will look to see that they have gotten through some hurdles. They have survived all the obstacles that are there. They've won a kind of a lottery, and at that point we will buy them. We will buy the whole company, or at least buy the product from them. And they have the resources to do that. I'm not criticizing that, but it does require a kind of change in the classical role that you normally associate for you're subcontracting R&D, in other words.
So it seems to me that a lot of the problems that you're describing really boil down to gaps in education, right? So like problems with the surrogate markers being misinterpreted, the biases in studies, and the interpretation and use of early screening tests. It really to me it sounds like it boils down to the statisticians that understand like sources of biases, correlations, and these things don't necessarily understand the clinical and medical issues that go into identifying those, and then perhaps some of the physicians that are involved in these studies don't have an understanding of the statistical implications of how the study is set up. I mean, it seems like a lot of the confusion that you're talking about in this talk has to be resolved at the level of education.
I agree. And I'm also at a stage in my career where I'm replicating what used to irritate me to no end when attendings or other elder statesmen would say things to me along the lines of, you guys don't even know anything about what it was like back in the day. And that invariably irritated me to an extreme degree. And so that is what I am saying now. You don't know what it's like back in the day. I think that what you're saying is 100% correct. I think some of it is an education issue. But I think that would be a simplification. Yes, education is the ultimate answer. But I like the Monty Hall problem because it is a warning. And I'm big on warnings. The Monty Hall problem is a warning that even exceptionally transcendentally brilliant people can miss a problem, can misunderstand the scope of the problem, and can misunderstand the format of the problem. Can miss that the problem essentially must be solved as a element of conditional probability and believe that it is independent probability. And I think that is how much greater education. We've had math professors miss this. We've had math professors not only miss it, but engage in highly vitriolic denunciations of those who got it correct. Right? Am I making this up? How much smarter can Paul Erdős be? Can you find the Paul Erdős, right? I mean, this is if they gave out Nobel Prize for mathematics. So I think the issue is, I wish it was that simple. I do believe it's education, but I think that, yes, you'll be able to educate, but I think the larger lesson is, and I don't mean this in a cliche-ridden way, though it may come out that way. I think it's good to examine the first principles of where a conclusion is going. What are the assumptions you are making if you say that screening is going to work? What are the assumptions that must come true, that must be true then? And that's why I broke that curve up by Laura Esserman and so on. Without saying it, it was that group C. You had to say that if you were going to do screening and it was going to work for a public health basis, it had to be C. The tumors had to predominantly be C, right? And if there were too many in A or B or D, your screening would fail. It'd be worse than failing. It would actually cause a certain amount of harm, because you're going to, once you go down the pathway, you can't do these things halfway. I know you authored the notion of what I call a statistical informed consent, and you were supported by learned colleague behind you, and I think that's true. I don't think that in a typical public health setting it will apply, in my opinion. I could be wrong, but if you have a new screening test for prostate cancer or a new test for breast cancer or something, yes, you can give the conditions and the caveats, but that isn't what, believe me, in my opinion, many patients will end up saying, doctor, will you just please sit down and just tell me bottom line, do I get the test or not? I don't want to know all this stuff. So the doctor then will have to then be in a position of evaluating it. But the doctor is going to require professional societies and various organizations. They're going to have to take the leadership role on it. And sometimes they drop the ball. So that's why it's going to be up to you guys to, at meetings and when you hear presentations and when you see public policy being made.
Education is good, but peer review is the checks and balances. It's not infallible.
It's not infallible.
Some dogmas can live longer than they should.
Some dogmas are self-perpetuating because there's too much invested in them. If,
in general,
yeah. I think peer review is good. If truly peer review by disinterested but not uninterested peers, and make sure that the person doesn't harbor some vendetta. We would not have done very well by some peer reviewers when we submitted the Human Genome Project. There would have been some peer reviewers to a moral certainty who would have said reject this paper, the one in Science. There's no question they would have said reject, and they would have found all sorts of great reasons why they weren't prejudiced or anything. It was just the science of it. So I guess there is that element, but I think education will certainly go a long way. Statistical literacy will go a long way. But I think each group is going to have, there'll be other problems that emerge.
Yeah, well, people are still going to be human. They're still going to make mistakes.
See, economics of this, the people who come up with these things want to come up with them. They make money from it. And the patient, when it comes down to it, I want to have every test possible. And so the two selfish actors kind of screw up the whole economic situation for society, it seems like.
Well, I would agree with you, except I wouldn't necessarily use the word selfish. I would say that these are people who have certain views, and it's, in the case of screening, it's just too incredibly beautiful and self-reinforcing to take the view that if you catch something early, it can't hurt and almost assuredly will do good. And that concept just goes against the grain. Now, in some tumors, that may 100% be true. I gave you some examples. I think in breast cancer, it's probably true screening does much better than. Thank you for coming. But I think for some tumors, prostate, the jury is still out. I'm sorry, there was a question back there. Did you still have your question?
I wanted to ask you about what the process was for developing AZV. What did you go through the traditional process of screening many compounds and
we did.
narrowing down? And
that was our brilliant method.
So you were the lucky lab who was the one who actually had one that worked out in the end.
Pardon?
So you were the lucky lab that you were the one, 10,000 compounds that actually worked out.
Well, we had an arm. We had a belief system that was actually opposed to the reality of the time, and I would have to say it's a very complicated story, but what we did not believe. Here are the four things that were true at the time. Many people believe retroviruses, pathogenic retroviruses, didn't exist in human beings at that time. Didn't exist. So why bother trying to treat something that doesn't exist? Two, even when it was acknowledged that some retroviruses existed, they thought they were like HTLV1. They worked in very rare conditions, very rare cancers like subacute T-cell leukemia or neurological syndromes. So AIDS has got nothing to do with that. 3. Even if all those other things might be acknowledged to be true, there was a belief that retroviruses were inherently untreatable. So basically, in other words, it's okay, it's a retrovirus, but it's inherently untreatable because they have a high error rate, and they have an extremely high error rate, and also they're integrated in the genome. So inherently, you can't possibly treat it. And then, in addition, there's a whole group of people that believed that vaccines were the only way to go, and there was just no point in trying to do drug therapy, that a vaccine would be right around the corner and solve the problem. That was 25 years ago. If you could believe the era that people believed that a vaccine would be simple.
So you're saying your lab didn't operate under the assumption that HIV or the symptoms caused by HIV were caused by a virus and stuff like that. You're saying that, so your lab, you were operating under different assumptions than we currently operate under for HIV. Is that what you're saying?
Well, I don't know what you mean. We accepted that HIV.
Okay, so
we accepted that HIV-1 was the cause of AIDS, and that a retrovirus was the cause of AIDS. We accepted. We did something novel. We accepted the data.
Okay.
The data were overwhelming. So then we said the only area where we had a strong disagreement was the view that it was inherently untreatable.
Okay.
We didn't believe that it was inherently untreatable. We believed that certain drugs, if they inhibited viral replication, would allow a plateau or a restoration of the immune system.
Okay. So you had a precocious view of HIV, I guess.
Well, I'd like to say that that I had Einsteinian foresight and was able to understand the universe in totality and could predict things without having to see empirical data. And I wish that were true. I think we had a belief system, we were prepared to test it, and fortune smiled. So it could have gone the other way. But I believe at the time, there was an inherent flaw in the thinking of the time, even for the vaccine advocates. And that is, at that point in time, depending on what statistic, you'd have 30 or 40 million people had already been infected or were about to become infected. And therefore, if you believed in a vaccine, in a classical primary prevention vaccine, you'd be leaving that number entirely to their fate. In other words, even a vaccine that was 100% effective in preventing new infections would leave tens of million people to die. And my position at the time was that that was ethically and scientifically unacceptable. And so we were going to take a chance. We believed there were data to support the notion that if you blocked retroviral replication, you would undo the virus's capacity to cause damage.
So AZT mimics like a nucleotide, is that what it is? Okay.
AZT is a nucleoside. Are you aware of a Sanger sequencing reaction?
Sure. Where you put in a dideoxy DNA.
Keep going. You're on the right track. That's perfect.
Right.
Yeah, and what does it do?
Well, it stops the replication.
Well, how does it do it?
Well, it lacks an oxygen or OH group, I think, to add another nucleotide.
Really good. It's a chain terminator.
Yeah.
It's called the chain terminator. It gets incorporated. That's the old way. You guys certainly wouldn't remember this, but there was a time when you actually had to, when you sequence something, you would actually put a dideoxynucleoside and look at a gel and look where it stopped. Okay? And it would actually stop the chain. And at that point, you knew that that was the incorporation, right? Soren remembers. You do not. You know automated DNA sequencers and stuff with electrophoretic capillary flowable things and fluorescent emitter diagnostic signaling and all that stuff. But there was a time when people actually had to hold up what amounted to an X-ray and do that. Well, that's what's being done to the virus, we think. We think the virus actually causes a chain termination of the virus and forces the virus to commit suicide. That's one operating. It's it. The virus, once that stop nucleotide is inserted, as the virus attempts to go from RNA to DNA or make the second strand of DNA, it stops. It's it. It's gone.
So you chose that specific chemical because you knew it had that effect. So you didn't try a whole library of chemicals?
We did try libraries of compounds because we were prepared for the notion that you could have unexpected activity. But once we recognized that AZT and other dideoxynucleosides could do that, and critically, that they would be anabolically phosphorylated, that is, the right phosphorus groups would be put on by the cellular enzymes, not the viral enzymes, the cellular enzymes. Once we realized, and we had to do experiments to prove that point, once we realized that, it was intuitively obvious to us that the drug, and could do so at a ratio that was much more damaging to the virus than normal cells by a couple orders of magnitude, 3 orders of magnitude. We believed very strongly that that would be clinically relevant. We believed that. That was the hypothesis we were testing. You need to have an intuitive, in my opinion, it is okay. It is required that you have some intuitive process when you frame a hypothesis. I don't think within broad limits, unless you're saying something insane or violates the laws of thermodynamics or something, you don't necessarily have to defend your hypothesis beyond a certain point. It's the proof of the hypothesis that you have to be highly objective about. There you have to stand aside and say, look, it's going to come out the way it comes out. There's nothing. I can't want it to work, and that will make a difference. So we came up with a hypothesis that drugs like AZT would cause clinical improvement for the reasons I just gave. If you block replication, the virus can't hurt you unless it's replicating. And so if you block replication, our theory was at a minimum, you would keep the patient in the state they were in. But hopefully, and this actually happened, you would also allow restoration of the immune system, and that has been confirmed over and over again. By the way, this is an issue with the AIDS denialists, or the HIV-1 denialists. I don't know if you've been following the New York Times, but there was a whole country that made it a policy belief that HIV-1 was not the cause of AIDS, and went further than that, essentially refused to support any antiretroviral drugs. And the consequence of that was not a scientific debate. It was not a minor anecdotal discussion or some sort of hyper-sophisticated point. The consequence of that was several 100,000 people died unnecessarily. because in the decade that there was that denial, the people weren't getting, or there were barriers to their access. And now the relevant government for the relevant country has completely reversed course and basically said, boy, we're sorry. And even in resource-poor countries, when you introduce these drugs, you actually get a drop in the death rate. It's not just something for resource-rich countries. And if you're interested in this topic, you should come to hear the talk I'm about to give.
Let me have the last question before we leave. In this class, we talked a lot about genome-wide association studies. There are so many steps and so we're developing a critical analysis of step by step. It seems to be an avalanche of new studies. How is a company like Celera looking up at the progress in genome-wide association? Should we be critical about this? Is it overselling, or you see major progress that is coming?
I think genome-wide associations are incredibly important, as are functional genomics. But they have to be viewed totally objectively. For example, there are more than one way to understand genetic interactions with the environment. You don't always need a genome-wide association study to make an important advance. And you have to accept information and data wherever it comes from. Okay? That's number one. Number two, you have to recognize that genome-wide associations have the problems that we talked about. They can give you wonderful things, but they can also give you problems. So you need replication. Number three, we need to understand that the genome-wide associations are really the start. They're not the end, even when they're well replicated. So yes, they're important and they teach you stuff, but what do I do if I have a genome-wide association and I find that there's something located in intron 10 of a gene, but I don't understand what that intron is doing there? What do I do with that? You see where I'm going on that? And some of the associations, while absolutely real, may suppose I have an odds ratio of 1.5, and the confidence interval doesn't cross 1. Well, that could be very critical, or it could be that I'm still on a long road before I can apply that medically. That's why I'm telling you, I'm giving you my doctor's perspective. For me, yes, I believe in basic science. I love the beauty of it. I think it's important. I don't think everything needs to be defined in terms of a medical application as the justification for doing it. So I'm not saying any of that. But I am saying that if you make a major commitment in a biomedical field, that one has to be highly sensitive to the productivity of that field related to the public health. And that has to be eventually by some quantifiable measure. Okay? Reduction in incidence, reduction in death rate, alleviation of some definable suffering or pain syndrome or something, loss of productivity or something related to that. It has to have that element of a practical application. And we need to keep that as the metric. I think genome-wide associations are certainly on the right track, but I don't think they can be the only answer, and I think we need other tools. Otherwise, you're going to have a genome-wide association. We're going to go back to what I'm saying. Okay, now you've rushed to the starting line. You see where I'm going on that? You now are beginning a 10 or 15-year journey. I can't wait for 10 or 15 years more. I'm down to measuring things by the month. Okay.